All right. Welcome back to this introduction to power electronics. This week we're looking at feedback loops, compensation, and stability. So this is just a reminder of what we're doing again. So we're basing our discussions on this DC to DC Book of Knowledge by Steve Roberts, which is available for free on that RECom website. And then we're meeting on Mondays from 5 to 6 p.m. And then I've got the schedule posted online as well. So these are just some knowledge check questions for the material from last week. So as a reminder, last week we looked at isolated topologies, efficiency, and regulation, right? So these are questions that should um, help you out in an interview type situation, and I've got the answers to them as well. So you should take a look back at some of these questions and see if you can answer them at some point. So last week we also had this solar panel project, which is kind of intended to power an Arduino Mega 2560. So it's taking a 12-volt solar panel, stepping it down to 5 volts, and then designing for 10 watts of output power. Um, and so I've finished the design and schematic, and I do want to get to the layout at some point. I think it would be helpful to walk through how to lay out these switching regulators because it can get a little bit complicated. But I do have all of my results documented here, so I'm just going to quickly go over some of this. So here is the solar powered Arduino project, right? And first off, we've got the objective. So we're taking the 12 volts from the solar panel, stepping it down to 6 volts with a buck converter, and then we're taking that 6 volts from the buck converter to 5 volts via a linear regulator. And these were just some constraints to get you started. So we're looking for 10 watts again, shooting for 90% efficiency at least, and then we want to keep it less than 100 square millimeters in area, and we want to make sure that whatever integrated circuit that we find is available on distributors such as Mouser and DigiKey. Um, and so here is the power tree from the Arduino Mega 2560. This is directly from the datasheet that's available online. Um, and so we can see from this power tree, if we look at the end of it, we can figure out how much current that the Arduino Mega is actually drawing. And so if you add up all of these different currents, you get about 560 milliamps of total current. Um, and then one thing to note is that the Arduino Mega 2560 board actually already has a linear regulator on there. There's this SPX 1117 M3, which takes in power up to 12 volts, right? So this is a bit of a redundant project that we're doing, but I think it's still good practice nonetheless. So going into the design of the linear regulator, so there's this LT1118 low dropout regulator, which could be useful, right? So it has a maximum output of 800 milliamps, which is above our 564 milliamps current draw of the Arduino Mega board. And it also has a fixed 5-volt option. So that means that there's actually a feedback network inside of the device itself. So we don't need any kind of external feedback network, which can be nice. And then at the time of writing this, right, there are 344 in stock on Mouser, and then these run for $8.60 in quantities of one. So um, this is pretty expensive, right? $8.60 is a bit much. So we could then compare that to what's already on the board itself. So there's this SPX 1117 that we mentioned before, and these are actually significantly cheaper, right? So these are 30 cents in quantities of one. And this is just, always good to consider different parts. And the first part that you pick is rarely the best. So we're just going to proceed, with designing based on this SPX 1117, just because we know that it works, right? The board itself actually uses it. And so we'll just run with that. And one thing to note, you'll always want to read through data sheets. Data sheets tell you how to use the device, right? These companies are selling these devices and they want you to use it and they want it to work. So here in the data sheet, it tells you how much output capacitance that we'd like, right? In this case, it's 2.2 microfarad. And we usually want some amount of input capacitance, but there was actually no specification on the input capacitance. So if you kind of sift through the data sheet, you can actually find example applications usually. And in this case, there's a 5-volt regulator, which has 4.7 microfarads of capacitance that we've got here, input capacitance here, and then 10 microfarads of output capacitance. So we'll just use that for our design as well. Because why not? Next up is the buck converter. So the buck converter, I use this Analog Devices Power Studio Designer online tool, which you can use by just tossing in your requirements. In this case, we're designing for our input, which is a solar panel, right? It's going from 10 volts to 18 volts. And then we're going for 10 watts of output power at 6 volts. So you can actually figure out how much current that is. And in this case, it's 1.7 amps there. And so this tool also allows us to tune the design criteria. I mentioned previously that we're shooting for 90% efficiency and then area under 100 millimeters squared. So here I've got my design criteria entered in using these little drag bar things. Right, and one thing to note is I tuned it for less than $1, but the chip that I mean, like the cheapest chip that they picked out was $8.30. So maybe it kind of just ignored the cost and ran with the other design criteria. But this was the cheapest switching regulator that I could find of the different parts that they recommended. So that's okay. We'll just go with that. There might be some cheaper options on TI or some other manufacturer of these chips, but this is okay for now. And so this is the design that ADI Power Designer tool spit out. And so you can see that a lot of the necessary part values are actually already calculated. The big ones being the inductor, right? So 1.5 microhenries, and then the output capacitance. These will determine our output voltage ripple effectively. And so one thing to note is it's always a good idea to make sure that the values that these tools generate make sense. So I actually haven't gone and done that yet, but in general, you'll want to make sure, through your own simulation that this actually works before building it up and trying to make it work for yourself. So getting into some of the other parts on this design that it was spit out. So there's a C1, which is a tracking and soft start capacitor. So these are used to prevent surge currents on the input supply. So when we turn on this buck converter, right, when we first turn it on, the output voltage is effectively zero unless there's some magically stored voltage on these capacitors. So it's usually at zero. And because it's at zero, the controller will try to send really large packets of energy from the input to the output, and this will actually cause a pretty significant surge currents. And so we don't want that. And one way that these switching regulator, converter chips make up for that, these large energy packets is by slowing down that the duty cycle, right? The rate of change of that duty cycle. We don't want to send these large energy packets right away, so we're going to slow it down. We're just going to add some capacitance on this soft start pin. And there is a example design, right, in the data sheet of the switching regulator, which uses 10 nanofarads. So we'll just go with that. And I didn't find much guidance on what other value you could choose for that, but I also didn't look into it very long. So maybe there's some in there. Next up, we've got our C2. This is another capacitor, which is actually just holding up a 3.3 volt power rail, which is used inside of the chip itself. So often, capacitors are kind of hard to make in silicon, so usually some of these pins will need some amount of capacitance to kind of help the chip out. And in this case, the datasheet tells us exactly that we need, at least 1 microfarad of capacitance there, and ideally a ceramic capacitor with low equivalent series resistance. And next up, we've got the bootstrap capacitor. So this is used to provide a voltage to drive the top side switch. So for those of you that are unfamiliar with how MOSFETs work, right? So these are the switches that are used inside of the regulator IC here, this controller IC. So MOSFETs have a gate, a drain, and a source. And in order to turn the MOSFET on, we need to supply a gate source voltage, which is above some threshold voltage, right, VT. If we're driving this topside switch with a microcontroller, for example, that's sending out 3.3 volts, right? Maybe this is a 3.3 volt little pulse that's being used to turn on the switch. Well, we can't actually do that because this gate pin is not referenced to ground, right? And so usually the source pin is actually sitting up at whatever our output voltage is, right? So in this case, it's actually sitting up at 5 volts, or actually, no, it's sitting up at 6 volts. So it's sitting up at 6 volts. And if we're driving the gate pin directly with the 3.3 volt source, well, then this gate to source voltage is actually negative 2.7, right? 6 minus 3.3. And this threshold voltage is usually never negative. It's maybe half a volt or so. So in order to actually turn the switch on, we're going to tap off of the output voltage, add some capacitance here, right? And so this is kind of what you see here. We're tapping off of the switch node effectively, right? And then it's going into the gate pin. And so this way we're storing some amount of voltage here, and that way we can actually help out the voltage that's being used to turn on the switch. So that's called a bootstrap capacitor there. You can read all about it somewhere. I'm sure if you look it up online, you read more about it. But it's effectively used to store some energy so that we can actually turn on switches that are not referenced to ground. Right, we need to get that gate to source voltage above its threshold value. And again, in this case, the datasheet tells us exactly how much capacitance we need. So we need just a 0.1 microfarad capacitor. And then I think this is a typo. They called it a boost capacitor. I haven't seen that anywhere. I've mostly seen it referred to as a bootstrapping capacitor. But maybe it's right. Who knows? Next up, there are a couple of feedback capacitors here, which are in parallel with our, 2 feedback resistors. And so these are used to compensate the feedback loop, and we're going to actually talk about this today. And so for now, we're just going to leave them empty, not populate them on the board, put in some placeholder values. Here I've got the buck stage in Flux AI. This is the schematic of it. We saw all the different values. We walked through how to find the values that were not directly shown on the tool. And then we've set in placeholder values for the 2 different capacitors there. And I made all of the little capacitors and resistors in the same 0805 package size. So this is usually a good size for actually hand soldering things, which we'll probably end up doing once we build this up. Um, and just to give you a sense of what this looks like, I'll just open it up in flux.ai here. So again, I'm on the schematic view and I've got my buck converter here. All right. And the nice thing about Flux is that it also has a PCB editor. So I've got all of the components here, and then the shape of the board. I'll be doing the layout probably next week so that we can go over it in a future video. But right now, the parts are just kind of floating around, and I haven't done anything with it. But anyways, and then this is the linear regulator stage, right? So it's tapping off of the 6-volt output of the buck regulator, and then it's spitting out 5 volts there. So the analog devices power designer tool also gives efficiency estimates, which is usually good to verify in the lab, right? We were shooting for 90% efficiency, and it looks like at our target current, we're getting about 95% efficiency, which is great. So that is just a recap of the project from last week. I'd encourage you to go through it and try to design it yourself or play around with it. Anyways, now just a project to reinforce the concepts from last week. So as a reminder, we looked at isolated topologies, and so this time we're going to design a flyback converter to power an Arduino Mega 2560 over Ethernet. So the Ethernet standard per IEEE, I don't remember exactly which standard number it is, but it's 48 volts. So, you know, those little Ethernet cables that are coming out of your modem, they're usually carrying 48 volts, I believe. And then I've actually gone and picked out a flyback controller chip for you to use this time instead of going in and looking for different chips to use, because this can get a little bit more complicated than just a buck converter and then the linear regulator. And this time we're designing for 2.5 watts of output power, which should be sufficient to power the Arduino, right? This is about 500 milliamps or so, half an amp. So should be enough. And just like this week, I'll go over a solution next week because we're not meeting next week. And then I'd encourage you to simulate it in LTSpice and then also go over the data sheet to get started. All right. Now getting into the material for this week. So starting off with feedback loops. So it's not usually practical to make power electronics or really do anything with open loop control. So this is kind of like having a knob and not being able to actually observe what it does in your like little control circuitry. But there are some cases where we don't necessarily need closed loop control. In this case, the book gives an example of a Royer oscillator, which exploits known characteristics of a transformer to just generate a square wave. Right, so we're taking this 12-volt DC bus. We've got some kind of transformer here, and we've got these two transistors, which are being used to excite the transformer windings in such a way that it creates a square wave. And in this case, it's going at 55 hertz. But of course, that's a little too simple for us. So we're going to be getting into closed loop control. So closed loop control is used wherever we're trying to really regulate an output. You know, in our case, we're trying to regulate an output voltage. And this is just the example of the buck converter, which, you know, we've seen time and time again. We're tapping off of the output voltage. We're scaling it down through this resistor network. We're feeding that through an op amp, which then generates an error signal by comparing it to some kind of reference voltage. And depending on that error, we are modulating the pulse width of, right, these little voltage signals that are being used to turn on our switch. And for example, again, when the buck converter output voltage is too low, which it will know because it's comparing the voltage continuously through this op amp, we're going to increase the duty cycle, right? We need some bigger energy packets, very simple. And the nice thing about these feedback loops, right, and this closed loop control is that it actually corrects variation in both the input and the output, right? So if the output is drooping too low, it's going to send bigger energy packets out. And when the input voltage is also drooping too low, right, the output voltage is in this direct path of, right, if we go from the input through the controller, right? So this feedback loop will actually compensate for the input voltage, any kind of input voltage variation or output voltage, which is very useful, right? That's why we use it. But one thing to note is that whenever we use feedback, it needs to be negative in order to remain stable. And so this negative feedback ensures that any kind of correction is actually opposing the amount of error. You can imagine if we have positive feedback instead, well, we're making the error signal itself larger, right? And this is bad because then the output voltage will start to amplify in turn with the error amplification. And at some point, the output's just going to saturate due to whatever physical constraints that you have, right? You can only go so high before things start to break down. And then this is just a note on control loop representation with block diagrams, because control theory is not necessarily a prerequisite for our discussions that we're having here, but it's good to be aware of these different representations of a control loop. So this is a feedback loop block diagram, which actually represents the buck converter schematic that we were looking at before, and we'll go through what these different blocks are. So starting from the top left, we have the reference voltage, which is being compared to the output voltage down here on the bottom right. Well, not necessarily the output voltage, but the output voltage, which is actually fed through this feedback network, right? And the feedback network has some amount of gain associated with it, right? We're usually scaling down the output voltage to compare with that reference voltage. Right? And so all of these blocks, apart from this little summing junction here, have some amount of gain associated with them, right? And these are denoted by these capital K sub whatever in either case. So this K sub EAS is the gain of the error amplifier. K sub mod is the gain of the pulse width modulator. And then the case of PWR, this was the power stage, right? So the switching FETs, the power MOSFET has some gain associated with it. And then the filter, which is our LC filter in that case. So this is just another way of representing our system as opposed to looking at it as a schematic. And so these block diagrams become useful when we're trying to figure out transfer functions, right? When we're going, say, from the input to the output, or from the control, which is output of this modulator, to control to output, right? Different transfer functions there. All right, and now getting into a little bit about discussion of frequency. So these LC low pass filters resonate at a certain frequency, and so this resonance creates a second order pole. So we've looked at what the frequency response of these low pass filters look like, and right off the bat, we usually look at the gain response first. And so each pole causes the gain to roll off at a rate of minus 20 dB per decade. And since this is a second order system, right, we have two poles at that specific frequency, which causes the gain to roll off at minus 40 dB per decade. And a decade, is just powers of 10. So, right, so if we go from 1 to 10 to 10 squared, right, to 10 to the third, these are decade steps. So if I'm at, say, 0 dB up until 100 hertz, then by 1,000 hertz, right, or 10 to the third, I've reached minus 20 dB, right? And so this is what this minus 20 dB per decade means, right? It means that we're decreasing at that rate exactly. And just as a reminder, 0 dB means that, so this is also called unity gain, and it means that all of the input gets to the output, right? So at 0 dB, if I have maybe right, again, if we had 100 hertz, 0 dB at 100 hertz, that means that if I had a sine wave with a period of 1 over 100, right, this is 100 cycles per second, then if I input this into my system, right, this is just say 1 volt sine wave, then that exact sine wave appears at the output. Now, typically, it doesn't appear perfectly in phase with the input, but right, it'll be phase shifted. It's usually lagging right behind the input, right? So we send it in and then it comes over at the output at a later time. And so that will be denoted in the phase response of our, frequency and analysis plots here. So this is the gain response. We also look at the phase response, and we'll get into that a little bit later. But now getting into this capacitor. So real capacitors actually have series resistance, which will slow down the rate of change of that capacitor voltage, right? And in doing so, this will create a zero, which will then increase the gain by 20 dB per decade. So here you can see this entire network here has a second order pole due to the LC filter right there. And then it also has a zero, right? Order 1, 0 due to the series resistance of the capacitance there, which will effectively bump up the gain by 20 dB per decade at that frequency. And since we were already rolling off at minus 40, we're now rolling off at minus 20. So I know that's a lot to take in, but if you read through any intro to circuit analysis textbooks, these will become clearer. So I'd encourage you to review some of that. All right, so that can kind of concludes our discussion on feedback loops. And now we're jumping into compensation. And so all of these kind of relate, so they're not just jumping all over the place. So control systems are often analyzed over frequency. And our ultimate goal, as we talked about before, is to prevent positive feedback. We don't want this positive feedback because it'll just cause the output to just increase forever and start to break down our actual system. And one thing to note is that we can actually design a system with negative feedback, but then all of a sudden it becomes positive. And this happens when the phase of the output reaches 180 degrees, or pi radians, and I've plotted that here, right? So here I've got sine of x in blue, and if we have sine of x plus pi, well, this is a sine of x just flipped over the x-axis, right? So this is actually negative sine of x. So whenever we reach this 180 degrees of phase shift, we are in a danger zone, right? This is bad because our negative feedback all of a sudden becomes positive and our system is at risk of breaking down. And so what we want to do is make sure that our gain at this minus 180 degrees phase shift is sufficiently low such that it's hardly impacting the output, right? So maybe I send in some, like a 1 volt sine wave, but at that specific frequency, right, we've got our minus 180 degrees phase shift, but maybe the system attenuates it, by like 40 dB, right? So we're effectively getting nothing out of that 1 volt sine wave. And so that's usually the goal, right? We don't want this positive feedback to hurt our system. So we attenuate it a lot. And a good controller will have sufficient margins. So there are two different types of margin. First off, phase margin. So phase margin describes the phase difference from minus 180 degrees at the gain crossover frequency. So again, this gain crossover frequency, or this 0 dB frequency here, is where all of the input gets to the output, right? And so we want to be way the hell away from 180 degrees because at that point, right, we've reached positive feedback. And we do not want positive feedback with 0 dB, right? We don't want this positive feedback to keep going around and around the loop. We need to get rid of it. So we introduce what's called phase margin. We stay away from 180 degrees at our gain crossover. And another margin that we like to look at is gain margin. And so this is the gain at minus 180 degrees of phase. So if we look at our phase response down here, where we've hit minus 180 degrees, we want to stay away from 0 dB, right? So this is our gain margin. If we're above 0 dB, we're really in trouble because now we're injecting huge amounts of positive feedback into our system, right? So this is how we measure the performance of a controller. We look at these margins. And to give you some reference, I think usually 20 dB of gain margin is desirable, and 45 degrees of phase margin is usually okay. So these are just, I probably should write those in somewhere, but whenever you're designing a system, you'll usually have some kind of constraints into the gain and phase margin that you're trying to do. It's usually flowed down to you, hopefully. And getting into compensation networks. So we saw the design from earlier on that buck converter, and it had some compensation capacitors in the schematic, but they didn't actually give you the values. And usually datasheets will tell you how to actually pick those values of your compensation network to achieve gain and phase margin, desirable gain and phase margin. And I'm not going to get into all of that today, but it's just something that, is good to keep in mind in general. All right. So now jumping into stability. So again, we have our gain and phase margins. We're trying to stay, stable so that we're not accidentally introducing positive feedback, but how do we actually go and make sure, that we're not doing so? There are a couple of different ways. So first off, we should always do this experimentally. Right? You don't want to design your system and just kind of say, all right, well, it should work, without actually going and measuring these margins. And so what you usually do is you use that's not how you spell analyzer. So there are these tools called Bode plot analyzers. For example, there's this Bode 100, which is very common. And so what these do, and a lot of oscilloscopes will actually do this as well. They have these Bode analyzer tools built in, but what these will do is they sweep over, you specify a range of frequencies that you want to analyze your system under, and it'll send sine waves into your system, usually through some kind of injection transformer. Um, so here in this case, right, we've got our channel one going directly into the feedback network, and then channel two measuring the output voltage, right? So we're sending in little sinusoids into our feedback network, and we're measuring the response at the output here. And this way we can generate the gain and phase plots. We can see how much the signal at whatever frequency we're looking at is amplified, right? So how much is getting to the output, and then how much phase difference, right? So maybe this is happening at, a later time, right? So it's always going to happen at a later time, right? So this is always going to be negative technically. But how negative depends on where that output sine wave appears, with respect to the different um, where it appears in time based on, with respect to the switching frequency itself, right? So we look at that period, the switching period, and compare those two. Um, so I guess just as an example, right? Maybe I inject a sine wave and it comes out over here, right? So what is that? That's about 90 degrees or minus 90 degrees, right? And if it appeared over here, that's 180 degrees, right? And so on and so forth. And then, of course, these different amplitudes correspond to the gain, right? So this is certainly a negative gain, right? We're less than 0 dB. If it was like all the way up here, or I guess let's take a step back here. We're all the way up here, right? This is now more than 0 dB. All right. Oops. There we go. And so we should also do it, right? Measure our stability mathematically. This is usually a first step, actually. Before doing it experimentally, we need to actually design the thing mathematically. And the first step in doing that is finding the system transfer function in the Laplace domain. And this is another thing that you'll need to refer to circuit analysis textbooks to figure out. But it basically boils down to changing the inductors and capacitors into the Laplace domain. And we have the impedance of an inductor, Z sub L, which is S times L. And then the impedance of a capacitor, which is 1 over SC. And then the impedance of a resistor is actually just R, right? It's just the resistance itself. So we go through and we determine the transfer function, and this transfer function that we find tells us where the poles and zeros are. And again, the poles will contribute minus 20 dB per decade to the gain, and the zeros will contribute positive 20 dB per decade. So these poles are where the denominator goes to 0. So if we're looking at this transfer function here, if we set this equal to 0 and solve for S, right, this is a quadratic equation. We've got an S squared. So there will be 2 poles, just as we talked about before. And then we have zeros in the numerator, right? So this is the numerator. If we set this equal to 0, this is actually pretty easy to solve, right? So this has a 0 at minus 1 over RC. Yeah, so once we have our poles and our zeros, we plot them on this S, right? We have real on the horizontal axis here and imaginary on the vertical axis. And we plot our different poles and zeros on here. Here, I don't know why it seems like they plotted everything as a pole, right? So usually when you have these pole zero plots, a pole will be denoted by an X and a zero will be denoted by a circle. But anyways, so anything in the left half plane will decay due to a negative real part. So again, here we have the real axis. So if we're on the left side of this imaginary plane, right, that means that our real part of our polar zero is negative, which means that we'll have some amount of decay. Whereas if we have something in the right half plane, it will increase exponentially effectively, right? So here, if we just have a zero in the right half plane, it's just increasing. I don't know why they have a X there. Whenever we have something with an imaginary component, it will always have a sinusoidal response. And so here in the top left, they have an example of this. So we have a decaying exponential because there's a negative real part and we have a positive, or we have some imaginary component. And whenever we have an imaginary component, i.e. it's complex, right? So this is a complex pole. Complex poles will always have a conjugate, which means it'll have something with a negative imaginary part here, right? So these poles, these complex poles will always come in conjugate pairs. But yeah, so right half plane is always considered unstable just due to increasing exponentials. And then whenever you have all of your stuff in the left half plane, you're usually good to go. And I think that's all I had to say. Yeah, that's all I had to say about stability. So I think with that, unless there are any immediate questions, I'll probably stop the recording here. All right.